Yeah, it is. So there's cells in there if you guys want to come and look. Only one microscope. So I'm going to pass around. This is the molds that we make in the classroom. Okay. This is the mold that we make here in the lab.
Just take a second.
So if you look, you'll see that they have little lines in the centers of them.
The cells.
So that's the part where we put the cells in. And that's used for printing onto different membranes or different slides. So we could fabricate tissue. This is just a stamp that we make, actual stamp that we use. The cells are in there. It's mainly biomedical.
You have to get a good.
So they do biopolymers. So those are my cells that you're looking at, and we're trying to copy them onto just regular glass slides so that we can kind of create tissue layers that will be used for heart transplant patients or people that have cardiovascular diseases to help repair their heart instead of having a transplant. Sorry, no, it's so squished. They actually If you can't see it, you can use the little ones on the side because my eyes are different than y'all's eyes. What are you, HCC or?
What's that?
Are you HCC or what community college are you a part of?
I actually work for the College of Engineering here.
Oh, cool.
UNK.
Can I see too?
Oh, yeah.
What type of cells?
Huh?
What type of cells?
Those are fibroblast cells? My cells? Not my kids?
Yeah, yeah.
So we're not supposed to be looking. They deal with I don't really recommend it.
When you look at what are you see?
What happens is that after a certain temperature, it collapses.
Okay, a second.
Yeah.
Oh, sorry.
What's your first lab you guys seen today? That's awesome. I got accepted to that college.
I wish I had asked Kimmy for her. She has a video of the cell. She has a video.
I just graduated here.
it's just like,
Okay, it looks like
Those are my cells, fibroblast.
3D layers.
mice.
Built on top of each other. But the video that they have is of
oh, when they
they all
Do you guys have any questions?
So what I'm going to show you here, I'm actually co-advised by Dr. Brasino, which is the Department of Biomedical Engineering Director. He heads up the Global Center for Hearing Speech Research across the street. I don't know if you guys were able to tour his lab. What he's basically focusing on is how people lose hearing over age-related hearing loss and treatment processes, as well as understanding the mechanism of how we lose our hearing. What I'm going to show you here is basically a project that my project is dependent on, but it's actually something that we just did as a test run to give you an idea of what acoustic waves do to nanoparticles. My project is trying to induce stem cells, which are your embryonic development stage. I don't know where you guys are along the
Does
process
anybody know
are.
what a stem cell is?
Yes.
Yeah.
What is it? Who can answer that? What is a stem cell?
The specialized stuff.
It's before it's specialized. So
You can be specializing in your way once.
Mm-hmm.
Yeah.
It's like, it's like,
So it can actually differentiate into everything that you see in your body now. I specifically am trying to differentiate embryonic stem cells and hopefully go along the path that will lead to hair cells that are found in the inner ear needed for hearing. So specifically, this is going to show you, and it's going to kind of test your hearing capabilities as well. But what I'm trying to show you here is basically, as you change the acoustic wave, you'll start to hear different pitches in the noise. These
3 kilohertz.
nanoparticles will start to form patterns. There's another graduate student, he's actually in Japan right now, specializing in something to come back with to finish his project, but he's trying to use acoustic patterning.
4 kilohertz.
I'm going to lower it a little bit. Yeah. He's trying to use acoustic patterning for cells to be able to grow in certain patterns. I'm trying to use acoustic waves to apply mechanical forces to the differentiation of stem cells. So we have similar projects. We did this as a test run, and you can start to see little nodal patterns as you get to higher frequencies. It's going to start hurting. If you're older, you're actually not going to hear certain frequencies.
What?
So. Any questions? Joel usually does this in person, but he's in Japan, so I thought I could show this work and kind of piggyback on it.
Probably doing the same.
But that's pretty much all we had.
So, why don't you tell them a little bit about your background, if you don't mind?
I started at community college. Actually, I started at 4-year, went back to community college, got my associates in chemical engineering. Then I transferred to City College of New York and got my bachelor's in biomedical engineering. I transferred here, got my master's in biomedical engineering, and now I'm doing my PhD.
Wow.
So I've taken the track that all of you guys are taking. It's a long track, but it's feasible. With hard work and determination, you guys will get there.
So, you did an internship. Where did you do your internship, and what did you do?
My first summer here, I did an internship at Corning Incorporated, which is upstate New York, specifically in their life sciences department, dealing with cancer invasion of 3D matrix, and basically trying to use a system that they were optimizing to understand metastasis and the chemicals used that are supposed to inhibit metastasis. Do you guys know what that is?
I don't know. What is it?
It's basically when the cells start to differentiate and go elsewhere and the cancer starts to spread. So there's certain inhibitors, kinase that they use to prevent spreading. And I was specifically testing that with their 3D optimized RGB platform that they sell. I was in R&D, mainly the research part of it.
So what do you want to do when you're done?
I'm still undecided. I want to either teach at professor's level or go back into industry and then come back to teach. I'm still getting my brains, and I'm going to be TAing in the fall to get a little bit more teaching experience to figure out what the teaching is for me. So I really enjoyed my internship, like industry, but I also like teaching. So we'll see what happens.
So anyone have any questions from the call?
How long has it taken you to get this far?
A long time. I graduated high school in 2002. I started right after high school at Rutgers University, went back to community college, graduated in 2004, then, 2004, then 2007, then 2010, and here 2015. So it's been a while. But I also have medical disability, so it takes me longer than most people. So it won't take you that long if you're more determined.
Yeah, but always remember this. It's not the length of the journey, it's what you learn along the way, and it's the people you meet who can help you to get where you want to go. That's what you have to think about.
Robotics lab, we have several labs around the campus. In this lab, we work on robotic manipulators for the most part. And we have several different projects that we've been working on. One is what we call the hands-free chairs. Who has the phone?
I think it's on my desk.
The one on the hat should still be on the hat.
So this hands-free chair, we've actually developed a few prototypes, successively, a little bit better each time. This is prototype 2. Prototype 1 is back there in the corner, the black chair. That one, the way that one works is, let me just let you know what this does. A hand-free chair is operated without your hands, no joystick. You use a phone to operate. The old one used to be, what were they, pressure sensors, Dan?
They're potentiometers.
Potentiometers, okay. And you literally would lean the chair. It's kind of sitting on springs. They remodified the chair. So you lean the chair, and that's what drove it. Well, we found, in a nutshell, I won't give you the details, that's not really great for people. So they came up with a phone app, and we use the phone to drive the wheelchair. This is used for people with disabilities, somebody who maybe quadriplegic, they can't move anything from their neck down. I'll show you how this works. So you can attach the phone to just about anything you want.
Use the other chair, that one's reversed.
Oh.
Or you can reverse it, I guess.
No, that's okay. So this is the third prototype. This is a slight improvement over that. The difference between this system and this, the driving system between the phone and the chair is the same, but what we did with this was we modified it so that we're not making any modifications to the manufacturer's wheelchair, so you can still use joystick. And you're not cutting into any of their systems, so you're not voiding the warranty. So what we did is we made this control system. It's basically that control system, and then we use a special harness. So they have plugs inside each one of these chairs that connect the computers to the motors and the batteries and all that. So what we did is we figured out what plugs they use. We made a special harness so that you unplug theirs, and then we plug our system into it. And when we're not using our system, all of the plugs do is just bypass through our system back into their system. So that's how I can use the joystick. And I haven't cut any wires. As soon as you cut a wire, you're voiding warranty. So that's why we did it that way. So all we have to do is we just hit this switch, and that switches to our system. I'll show you how that works. Just give me 1 sec here. You turn this. You turn this around. We did, didn't we? Let's turn. That's okay. So let me stop it.
Like the screens.
So this is hat. It's got turned around. So we'll turn it around. I'll show you how you can use this with just a hat. You can hold it in your hand, but obviously it's kind of like what's the use of doing that? You know, I can use the joystick. So it's more for like if you have an amputee or something, you have an arm strap to your arm, and then just by rotating it, you can control the chair.
Oh, I don't know about that, but I'm still holding it in my hand.
So you just lean in the direction you want to go and drive the chair. So what we do is we take your phone. You know how your phone always knows like which way it is? There's accelerometers in your phone. Those are the little sensors that tell it knows, you know, where your orientation is. So they're constantly reading out data with this accelerometer. So we take that data and we convert it into usable information for us so that when we move, it moves the chair. And the speed is determined by the angle that you tilt your phone. So if I tilt it a little bit, it moves slowly. If I tilt it a lot, it moves faster. See? So the degree of tilt determines the velocity. So you can completely control your speed and obviously direction. Hands free. So this is one of our projects.
Here's the first prototype.
Now, Dan can operate the first prototype. He's the only person who can operate the first prototype. He's actually gotten quite good at it. He makes it look easy, but I've worked on the project a lot, and I've tried, and it's not the best. The springs are kind of getting worn out. At first, when they first made it, this is what, about 7 years old maybe, and when they first made it, the springs were tighter, and what happens is because the springs have gotten loose, as soon as you start to lean, it wants to go all the way. Well, you can imagine what that does to the driver.
And you also
Throwing
need
off the chair.
stronger leg muscles or leg control to actually push it back to the center position. Or even if it was strong springs, you would still need those leg muscles to push against the springs, which kind of makes this not a very viable solution for a hands-free chair.
And this is much more so, being a phone, everybody's got a phone. So this is one of our projects. Another one of our projects we've been working on is this is a gripper, otherwise known as an end effector. It goes on the end of any arm, robotic arm. And what we've been working on is making this so that it has sensors in there, so when it goes to touch something, it feels that and sends that information back so we can stop it. So it doesn't smash things. As you can imagine, robots are pretty strong, and we all know that what they are. And if this is going on an arm that's going to be used on a human, we want it to be able to sense what it's grabbing and how hard it's grabbing something. So we've been working on that. It's not hooked up right now, so I can't show you the demo. It doesn't work. We just have been working on some other modifications. But the sensors, what they'll do, they're so sensitive that we can literally grab an egg without pressure. And we all know just how delicate that's like. We've all tried one before, I'm sure everyone did. So that's another project we've been working on. We're also making it so that it's very user-friendly for people that are not computer science people, and that there will be a user display that will be on your computer that's very user-friendly, move this bar with your mouse or that sort of thing, versus programming, which is that's the stage it's in now. You can use it, but you got to know how to program. A lot of us don't. So we've worked on making that very user-friendly and gotten quite far. Still a work in progress. A couple more projects we're working on here. This combination of robots, this is Baxter, and this is another separate robot that we married together called PowerBot. Together we call it BaxBot. And this does, we were doing a lot of things with this. These gentlemen can tell you a little bit more about them.
Yeah. So some of the projects that we're working on, they still require a decent amount of interaction from the user. Like the WMRA, for instance, one of the things we have is teleoperation. So you still actually have to move it. You still have to drive it around with the joystick. This one, the goal with this system was full autonomous actions. So what we have here on the top unit, it's Baxter. It's called Baxter. It has these 2 7-degree freedom arms. And then it also has a wide range of sensors. So it has these sonar sensors at the top, so they light up whenever somebody gets in front of them. There's also sonar sensors on this base unit here. So when it's driving around, this can actually, it can navigate around the house automatically. It's because it has this laser sensor also in the front. So it can tell the distance to any wall, and it can figure out based on what it sees where it is. And it can find it, you can map out your whole house so it'll feel like in your bedroom. You can tell it to go to the kitchen. You don't actually have to physically drive it like you would with like the wheelchairs where you have to actually drive it. It will automatically find its way to the kitchen and avoid obstacles along its way there. Another thing that we use are these Kinect cameras. And what these allow us to do is, so what they allow us to do is that they allow us to see the environment in 3D. So with a regular, 2D camera, you can only see, just the image. The 3D cameras actually give us depth information too. So they show us how far away it is. And this is useful for like, if you told it to get you something from the fridge, it will know exactly how far away, that soda bottle is. So when the arm goes there, the arm knows how high it has to go, how much to the left it has to go, and how far in it has to go. That's a big deal for us. So So we have, there's one here that looks out into the environment, and there's one here that looks out into the workspace. So it used to be changed here, but it kind of fell off. It's back here now. But those aren't permanent makeshift. This is one of the latest projects that we have, so that's all subject to change. One of the demos that we do have, though, that we're going to show you, is the Connect 4 demo. So another thing that's inside each one of the arms, there's these 2D cameras. So there's one here, and then there's also one with the left arm. And you can see, I can follow and we point it at the board, the little game board, and we can segment out where the corners of the board are. And what that will do is that it will grab the actual board and split it into the grids where each piece is. And then it runs a color filter on there to figure out where the yellow pieces are and where the where the red pieces are. So that's what these two windows are. One for red, one for yellow. And using that information, we feed it into an algorithm that can, you can sit there and actually in less than a second, it can think about the whole game. It can think about every move you can do, every move it can do in response, every move you can do in response, every move it can do in response. It can go all the way to the end of the game. And it can think about which path, it's called the min-max algorithm, where it's trying to minimize your wins, maximize its wins, minimize its losses, maximize its wins. So it tries to play the route that has that much, the least amount of losses, the most amount of wins at the end of the route. And it will automatically update according to the current state of the game. So I'm going to start the scan up.
Want to play a game?
So who wants to play?
I'll go.
So what's your name?
Yeah.
Here's one thing. Another thing you actually, that's really important about this one, this is like some of these other little ones here, that this one's actually safe to interact with. So if you push on this, it's very easy to move. Like you can move it with one finger. Whereas something like this, I can put my entire weight on it and pull it, and it's not moving. And if this thing were in action, we would actually need to rope off this entire area, because if this thing hits you, it doesn't know. It has very little force feedback, and it's made out of solid metal. If this thing hits you, it actually can read the joints. They all have absolute encoders. So it knows exactly how much each joint is rotated at any given moment. So if it notices something's not moving, it knows it's hitting something, and it can actually stop. So very easy to move, not easy to move. Yeah. All right.
Hello, piano. Ready to get deeply at it? I can move ahead 1, 2, 3, 4 moves. How hard do you want me to try?
So we cap it off, so it doesn't go all the way to the end of the game. So basically, what difficulty do you want 1 through 4?
Easiest.
I heard 4. Yes.
We're going to try it.
All right, we'll try.
Not she's scared of me. Who wants to go first?
You go first.
My move.
We mounted the board onto this little thing so that we can actually drive it around and challenge random people to play it. But unfortunately, it's sort of been drooping. So I tried fixing it with this little table configuration, but if it drops pieces, if this thing moves just the slightest amount, see, it got it that time, but these slits are so narrow. If it moves the slightest amount, it may not get the piece in. So I apologize in advance if that happens. I tried my best to fix it.
Your move. My move. Your move. My move.
So 3D printing is becoming more and more popular nowadays. How many of you all had any experience or come in contact with any 3D printed stuff? Oh, nice. So all of you. This green slide here is actually a 3D printed device that we needed to make for Baxter.
Also, the paddles on the gripper there, they're 3D printed at least 10 different times because